This is about the constant volume process when dealing with water. So, unlike in ideal gas law, when we're dealing with constant volume process, we use the general gas law, which is the PVMRT. Here, in the constant volume process of water, we rely mostly on the first law of thermodynamics. So first, to describe you the constant volume process is first, let me draw the PV diagram for the constant volume process. So here, so our volume here is volume 1 is equals to volume 2. So dealing with the constant volume process, first is our work non-flow, which is equivalent to the general equation of P, integral of P dV from 1 to 2. Okay, so since in our process we have a constant volume, it means we have no volume change. So our difference for volume, so V2 minus V1 is equivalent to 0. So if our dV is 0, then our work non-flow should be also 0. Then next is our heat transferred, or let's symbolize it by letter Q. So let's derive our equation from the non-flow energy equation, which is Q is equals to the change in internal energy plus the work non-flow. But since we have a constant volume process, our work non-flow is 0. Therefore, our heat is equivalent to our change in internal energy. So, since we're dealing with specific internal energy, let's say that our heat energy is equivalent to the mass times the specific internal energy. So let's move on for our sample problem. So example number 1, a certain quantity of a 30 degrees saturated water is injected into a 0.3 cubic meters evacuated drum and then heated until pressure and temperature became 20 bar and 30 degrees C. Determine the mass of water used and the heat required. So in this problem, we have a certain quantity of 30 degrees temperatured water. So it is a saturated water. So that is our TSAT, which has a volume of 0.3 cubic meters. So what do we want to do is we want to heat that certain amount of saturated water into the pressure of 20 bar and a temperature of 300 degrees centigrade. So first, we all know that the state of our water is in saturation state. So first step is we need to find the properties of the water at state 1. Then next is find at state 2. So we're gonna use our steam table to find the properties of water at state 1. So here is our snippet of the steam table. So our given, so since we have a saturated water, we have to find the properties at the saturation liquid state. So first is we need to find the specific volume and the specific enthalpy. So the specific volume for 30 degrees C. So at saturation temperature of 30 degrees C, so we have to find our specific volume and this specific. So looking at the steam table, our specific volume VF is 1.0043 times 10 raised to negative 3 cubic meters per kilogram, and our specific internal energy is 128.78 kilojoules per kilogram. So now at point 2, we have 30 bar or 2 MPa and 300 degrees centigrade. So first step, we need to determine the state of our substance or the working substance. So to determine the state is first we need to look for the pressure for the saturation temperature at 2 megapascals. Our Tsat is 212.42 degrees centigrade. So our given temperature is 300 degrees C. So 300 is greater than 212.42. Then therefore, we could conclude that our state 4.2 is superheated steam. Finding the values for 2 MPa and 300 degrees C, we have U is equals to 2,772.6 kilojoules per kilogram. Now, after we collected all the values we needed, we can now solve. We can now proceed to solve for the mass, for the missing mass of the fluid that we injected on the evacuated drum. So for solving for the mass, we have our specific volume from point 1 here. So we all know that specific volume is just equivalent to the reciprocal of the density, which is volume over mass. So using this equation, we have 1.0043 times 10 raised to negative 3 cubic meters per kilogram is equals to the volume, which is given as 0.3 cubic meters all over our mass. So our mass now will be 298.7155 kilograms. Then, after finding now the mass, we can now solve for our heat needed to, or the heat energy needed to reach the temperatures and pressure at the second state. So, Q is M times the change in internal energy. So, our mass is 298.7155 kilograms multiplied by the U2, which is 2,772.6 minus U1 of 125.78 kilojoules per kilogram. So, cancelling the kilogram, we can now solve for Q, which is 790,646.22 kilojoules.